Hey there, welcome back. This is Professor Roldan with Intermediate Algebra. This is section 15.7, and this is actually one out of 2 units for the last unit of the course that we currently have for Intermediate Algebra, and it is called chapter 15.2. Part 2, which is just going to be 15.7 and what we call Appendix O in your textbook. So 15.7 is what we're going to talk about today. This is functions. And Appendix O would be complex numbers. Okay, so let's go ahead and get started with 15.7 functions. Okay, so what are functions, guys? Well, functions are actually one of the most important ideas in mathematics. It's very foundational in equations and modeling the real world. All right, it gives us a vocabulary that can be transferred to a variety of applications. You got computer science, natural and physical sciences, analytics, statistics, and many, many more. So, first of all, we need to identify functions. A function is a special correspondence between 2 categories. Okay, so there's 2 categories, and we have a special correspondence. For example, each college student, there is a corresponding ID number. Okay, makes sense. Each item in Target is going to be related to a corresponding price. Okay, so without the ID numbers and without the prices, these two will be chaotic. All right, this is what makes things organized and understandable. So, for example, another one in number theory will be for each number, let's say 1 through 5, there is a corresponding cube of that number. Okay, so every number has a cube that is raising it to the 3rd power. Okay, so there is a matchup of concepts, and so we're going to talk about the first set of numbers that we've just talked about right here, the first set of ideas. Right before this comma, that's going to be what's called the first item, which is the domain. Okay? And then the second set, which is after the comma, all right? The second set of ideas after the comma is going to be called the range. Okay, so the first set is called the domain, and the second set is called the range. All right. So we can split this up. So it'll be domain over here, and over here would be the range. Okay. And then if you look at the diagram to the right, we can see that we have domain is the first concept, which corresponds to the second set of numbers or ideas that we're going to call the range. Okay, for correspondence to be a function, so now we're going to a definition here. Each element of the domain corresponds to exactly one element in the range. Okay. So, if you look over here to the right, we see that every single element in the domain, okay, corresponds to something on the right. All right. Now, there are situations where this is not true. Okay, so that, and we'll see that in a minute. And if it's not true for what we just talked about, each element of the domain corresponds to exactly one element in the range, then we have a problem, and that's the fact that it's not a function. So if you look at the first case, all right, this is called the function f, okay? And the function f, as you can see, are some things in the animal kingdom, including humans, that run, and you can see how fast the cheetah runs, the human, the lion. Okay? So the cheetah, the human, the lion, they all correspond to one element in the range. Okay? So in this case, this is a function. Not it, should be f. F is a function. Okay? Now, if you look at G, here is a different scenario. Okay? If you look at the function G over here, you will see that we have, in the domain, we have cities. Okay, so New York, St. Louis, San Diego. And in the range, we have baseball teams. Okay? So if you look at New York, okay, New York actually corresponds, New York belongs to two different categories. Okay, New York is not corresponding to exactly one element in the range. New York is corresponding to two elements in the range. So New York corresponds to the Mets and the Yankees. And this is what we call, or this defines something that is not a function. This goes against the definition we just described. Now, to help you remember this, I want you to remember the picture that this creates. When something is not a function, you're going to, in this chart, basically New York repeats itself. Okay? So if I were to take this arrow away from this, I would write another New York here. And let's say I'll draw to the Yankees. So that means, as you can see, the domain repeats. This right here, so there is one element in the domain that repeats. Okay? And if it repeats, then it goes against this definition that we said over here, where each element of the domain corresponds to exactly one element in the range. So this element, New York, corresponds to two different elements in the range. So that means that the domain repeats. And so an even further illustration of that, notice what this symbol is looking like. Okay? So you can see in the chart, this means that X repeats, or the domain repeats. And this is what we call less than. Okay, so that can kind of further help the whole repeating domain element of New York in this case. So when you see less than, that is not a function, okay? Let's take a look at a different example with the opposite illustration here. So if we take a look at function h, as you can see, 3 corresponds to 5, 4 corresponds to 9, 5 corresponds to negative 7, and 6 corresponds to negative 7. Okay? So, as you can see, the domain, they're all different. So you got 3, 4, 5, 6. There's no repeating domain values here. Okay, there is negative 7 that gets repeated here in the range, but that's okay. Okay, so this is a function. This agrees with the definition. H is a function. Okay, so we can say, why is it a function? 2 reasons. No repeating domain values. Okay, that's the technical reason why. But visually speaking, look at the picture that it's creating here. Okay, this is okay, and why this is creating the greater than symbol. Okay. And when you see the greater than symbol, you can just remember that it is a function, okay? It is perfectly fine. Now, before we do P, just want to point out that why are we even talking about this? Well, functions basically make more sense in real life. So, for example, we talked about, each item in Target. So let's focus on this for a second. Each item at Target, there's a corresponding price. Okay, that makes sense, right? So if you come over here, so let's say these 3, 4, 5, and 6, those are different products. Is it possible to have 2 different products, okay, 2 different products have the same price? Yeah, you could just coincidentally have a pair of shoes that is the same price as a t-shirt. Okay, that makes sense. That is okay. We function normally with that. But with this scenario right here, this does not make sense in real life, because again, if this is our products here, all right, you have the same product that has 2 different prices. That does not make sense. That would create chaos in the store. Okay, so when things are not a function in real life, it wouldn't make sense. So the same product cannot have 2 different prices. Okay, and that's what this less than symbol pretty much does. Okay, so let's say you went to Target and you see the name, the tag of the products, and then you see 2 prices listed. You're like, okay, which one is it? Well, that doesn't make sense. That would just cause confusion in real life. So functions make sense in real life, and things that are not a function really don't make sense, because it just causes confusion. So again, if you see the less than symbol, that's not a function. If you see the greater than symbol, this is a function. Okay. Now let's take a look at P. Why don't you think for a few seconds here and determine whether this is a function or not. Okay. So the question is: are there any domain values that are repeated? And visually speaking, do you see a greater than symbol? Because if you do, it is not a function. All right, so just take a few seconds to look at that and see what you come up with. So pause the video and I'll give you the solution in a minute. Okay, so hopefully you said yes, P is a function. Why? Well, as you can see, there's a 2, there's a 5, there's a 19. None of those get repeated, so there's no repeating domain values. And the visual is that we have this greater than symbol. You can see it right here. There's a greater than symbol, which it says it is okay in terms of defining a function or not. Okay, so if you have any questions, let me know. We're going to move on to the next page. So next we have example number 2. And again, we have a couple concepts that we need to kind of organize and see what's going on here. So sometimes you can make a chart and just create your own scenario. Okay. So let's make a chart. So we can make domain as the first values, the range is the second values. It says, is this a function? We have a family. All right. So what do you have in a family? Normally speaking, you have a mom, a dad, brother, sister, for example. This is a quick example, okay? And then for the range, you could have, okay, so let's talk about the person's age is the correspondence. So we have some positive numbers. So we have, is it possible that they all have a different age? Yes. Is it possible that mom and dad have the same age? Yeah. So this is make this a little bit more interesting. Okay. Sometimes the mom is, sometimes the mom and dad have the same age, my bad. And is it possible that they had twins? And so let's say the brother and sister are both 20 years old. Now, if we draw the correspondence, we got the greater than symbol, that's okay. Another greater than symbol here, that's okay. Okay. It is okay for range values to repeat, but not the domain. So this is a function, okay? So the relation between family and person's age is a function. Now, let's take a look at the set of all states in the United States. Correspondence will be cities in each state. Okay, so this is going to be quick because we can immediately find some problems with this. So D for domain, R for range. And let's just pick our state that we are currently living in. And we go to school here in Lakeland and most likely live here. And then there's the closest bigger city would be, let's say, Orlando. So just looking at two cities, we can already see the relation between those two concepts. That's creating the less than symbol, all right, which is not a function. And that means that Florida gets repeated twice. Florida goes to Lakeland, Florida goes to Orlando. So this relation is not a function. Okay, it's not a function. Because you can see the less than symbol, Florida gets repeated. You You're not allowed to have repeating domain values. All right, enough with definitions. Now let's go to actually what is the practical use of functions. So let's take a look at the next section here. So the next section is about finding function values. Most functions considered in mathematics are described by equation, which can then be represented by graphs. For example, y equals 2x plus 3 is a linear function. Okay, that's the one that we studied for the most part. And then we've studied this one as well, the quadratic function. Okay. So first semester algebra or the introductory algebra is going to go into linear and quadratic. Okay. And how to solve those and also how to graph those. Okay. So the reason why this one's called linear is because there is a power of 1 on this x. Okay. And the reason why this one is called quadratic is because there is a power of 2 on this x. Okay. Which makes the function behave differently. All right. So before we do this, I want to talk about so how do we connect what we just talked about in the first section with this section? Well, we introduced the words domain and range, and we said it's the first coordinate, or is the first value, and the range would be the second value. So we can actually put them in a pair now and say, hey, first, second. Okay. Well, this is going to relate to what you already know, that when you plot points, you have x values that are first and y values that are second. It's the same thing. So that means that the domain values are the x values and the range values are the y values because they're both in the same position. And this is going to lead us to some new words, which is going to be x, or the domain is also can be called the input. And then the y, or the range, will be called the output. Okay, so what do we mean by input, output? Let's take a look at the idea of a machine here, okay? So a function can be thought of as a machine that takes input, all right, which is the first values or the x values, and returns or produces an output, or the y values or the range. Okay? So we have done this before plenty of times in this course, where we evaluate an equation, we plug in items for x or numbers for x, and that will produce a certain y. Well, it's the same thing here. The only difference now is that we're going to be using function notation. In other words, we're not going to use the y. Okay, so now we're going to use f of x. Okay. So note that f of x is read f of x. So this notation, f of x, is not, so this right here, this is not multiplication. So what I mean by it's not multiplication, that does not read f times x. That is f of x, and that all that's saying that there's a function machine called f, and the input value is x. So let's take a look at the function machine. So we have the input value, what we're going to call x. This is going to go into the machine, And the machine is going to do a couple of things here, because that's what the equation reads. So the equation, or the math side of it, is going to be one side. Okay? So when we talk about equation, that is just the part that is basically the instructions on what to do with that x. So the instructions in this case would be, take that x, which is the input, multiply it by 2, and then add 3 to it. Okay, so 4 times 2 would be 8, and then 8 plus 3 would be 11. So that is what the machine is doing. And so if you put in a 4, you're going to get an 11. So the end result looks like this. Okay? So this is saying, if we take the function f, we input 4, we're going to get 11. Okay? So if you input 4 into this function called f, you get 11. Okay? So normally we would say, hey, if you put in x is 4, y is 11, that's your coordinate. This is your point. Okay? So this is pretty much the same thing you've done before, except it's a different look now. Okay, so let's take a look at the next page to see how this is different. Okay, so let's take a look at example 3. Find the function values for the function f of x equals 5x minus 3. Okay, so what the first one is asking is that we input a 2. Okay, so this is our input. If we input 2, what do we get from the function machine? What does f equal? Well, we need to put the 2 right into the machine. Okay, so replacing x is not something that's unfamiliar. All right, we've been doing this the whole course. Now it just looks different. Okay, so we do the calculation and we say, okay, this is 10 minus 3, which is 7. Okay, so the conclusion then is that f of 2 equals 7. So we can also put this in an ordered pair, because the input value is the first value, or the x value, and the output value is the second value. So this will be 2, 7. Okay? So go ahead and try the next 3 on your own. Actually, the next 2, and then I'll do letter D with you after we check your work for B and C. All right, let's go ahead and get that done, and pause the video and see your solutions, see if they match. All right, we're back, and hopefully you have what I have, and that will be that f of negative 3 is negative 18. Okay. And f of 0 will be negative 3. Okay, right here. So this is our coordinate. Okay, our ordered pair. Now let's take a look at the fraction one. This is actually going to work out very nicely. Whoops, I did that wrong. So we have 1/5 inside the function machine. Actually, the 5 and the 1/5 cancel each other out, creating just 1. And that 1 minus 3 is just -2. Okay, so f of 1/5 is going to equal -2. And we could actually plot that if we wanted to, as such, okay? Now, let's take a look at graphing functions by plotting points, which is basically creating a table, and we've done this before. So the first question is, graph the function f of x equals 2x minus 1 by plotting points. So we can do a table. And instead of putting f of x for I'm just going to put y. Okay, that's what you know, and that's perfectly fine. All right, so when we plot, we want usually 3 things, and it's going to take us 3 points. We want the left part of this picture. We want the right part of this picture, not just the right, not just the left, both left and right. And we also want the middle, and the middle is usually going to be 0, okay? Which is actually the easiest one. Okay, so we have left, right, middle. And so numbers that represent left, right, middle will be -1, 0, and 1. Okay, so this will be the left side of the picture, the middle, and this will be the right side. Okay, so we're going to go ahead and put -1 into the function. We're going to put 0 inside the function, and we're going to put 1 inside the function. Okay, so let's start with a -1. -1, that's going to be -2 minus 1, which is -3. Okay, which means that our point that we need to plot is -1 for the input, -3 for the output, or -1 for the x, -3 for the y. Let's go ahead and put 0 in here. That's going to create 0 minus 1, which is -1. That was the easiest one. And zeros just make the x term disappear, all the x terms. And then this one is just going to be 2 times 1, which is 2, minus 1, which is 1. Okay, so we can plot this -1, -3, which is here, 0, -1, and 1, 1 is right there. So we want to go ahead and connect the dots. And we have the left, middle, and right side of our picture. Okay, even though you knew how to do this using y equals mx plus b shortcut, this just shows that you can use function notation to create a chart and plot those points that you come up with. And this goes for any function, including functions you may not be familiar with. So let's take a look at function g in the next example. And in function g, we have an absolute value sign. All right, so g of x is going to be an absolute value function. Okay, so this one was linear, a linear function. This is going to be an absolute value function. So remember, absolute value just basically means, oops, it's going to turn all negative x values into positive x values. Let me put this over here. All right, so let's say, for example, you decided to only show the right side. Let's say the middle and the right. So you decide to yourself, I don't like negative numbers, so I'm gonna do 0, 1, and 2. Just because you can pretty much choose whatever you want for the x's. So then you get started and say, okay, I'm going to do I'm going to put in a 0 here, I'm going to put in a 1, and I'm going to put in a 2. So you go ahead and start calculating, and you say, well, that's 0 minus 2, which is negative 2. And then you get these values over here, and you get 1 minus 2 here, which is just negative 1. And you do the same thing for this one. It's just 2 minus 2, which is 0. So let's say you're creating a chart because you can choose whatever values for the x that you want, and you're just going to find the corresponding y value. And you go to graph, you may say, hey, this is just a linear function. I'm just gonna connect the dots and go on my merry way. But as you can see, guys, we did not choose a number that represents the left side of the picture. So actually, this is going to be wrong. Because if we actually choose a negative 1, like I said, we need the left, middle, and the right, not just one portion, because then you're going to not show the whole thing. So if we go ahead and put this in here, so the absolute value is going to make that negative 1 a positive 1. Then we subtract 2 and we get negative 1. So this time we have negative 1, negative 1. So if we go over here and plot negative 1, that's actually right there. Okay, so we see that we did the wrong thing by assuming that it was totally linear. And let's do another one. Let's do negative 2. So we put the negative 2 in here. That's going to turn into a positive 2 minus 2, which is 0. So negative 2 comma 0. And if we go back and plot this, that would be right here. So as you can see, guys, the correct graph, now that we have the left and the right side, is a V and not a line. Okay? So make sure, again, you pick a negative value, positive value, and something in the middle. Or else you may get the wrong graph. Okay? Alright, let's take a look at the next page. Okay, so this is the last page for 15.7, and this is about basically how to graph on MyLabs Plus. You've done some of these before, but it says on MyLabs Plus, you will need to first select the correct graph based on the based for the function you are given, and then find 2 points or more to form the graph of the given equation. So if you look at this, all right, you can tell that this is linear. Okay, that means you're going to have an x to the first power, and it's telling you need 2 points. Okay, you can see the 2 dots there. All right. Now this right here is the absolute value. Okay, which is an x to the first power in absolute value bars. And you need 2 points as well. If you have an x to the second power, and that's going to be your quadratic, and here, because there's 3 dots shown, you need 3 points. Okay, so this one you need 4 points. You won't be using this. This is 2 points, so on and so forth. This is actually x to the third, and this is a circle, which is actually x squared plus y squared equals r squared. So this is shading for inequalities that you're not going to be using anyway, so you just be using a few of these buttons here. Now, here's the last thing that we want to talk about, and that's called the vertical line test. Deciding if a graph represents a function, determine if the following graphs represent a function. So basically, we need to take a look at the vertical line test. Oops. The vertical line test tells us that a graph represents a function if it is impossible to draw a vertical line that intersects the graph more than once. Okay, so this is, what do I mean by a vertical line test? All right, so we're going to draw a vertical line, and it crosses only once. So that's good for as far as determining whether it's a function. Because if you go back to our study at the beginning of this section, we talked about x can only be listed once. It cannot be repeated. No repeating x's. Okay? So the vertical line test is going to kind of do the visual of that. So here we have one x. Here's another one that passes. But then once you get to this section, if you draw a vertical line, it crosses actually 3 times. 1, 2, 3. So that means the same x value is going to get repeated 3 times. All right, that is not a function. So this fails the vertical line test. And the conclusion is that it's not a function. The graph is not a function. If you look at B, this passes. Anywhere we look, it's going to pass. So this one passes, and this is a function. This graph is a function. So why don't you take a look at C and determine whether this is a function, okay? So what I recommend is looking at it and just saying, will there be any place where I will intersect the graph more than once? Well, there's not, because you can look, there's nothing, there's no x on top of each other. There's no graph. The graph does not fold on top of each other. We are not going to be repeating any x's. So this is a function as well. So this passes. This is a function. Okay? So that's basically it for 15.7. So just a quick recap. We looked at identifying functions, no repeating domain values or x values. And so that would look like a greater than sign. And then the less than sign was the one that is not a function. So again, we can connect that to this. If it fails the vertical line test, again, it's not a function. And we also looked at inputting values to calculate the output, or basically calculating the y function, the second value. Okay, and then just using those concepts of input output to create a bunch of points for any function and to graph it. So that's basically it for 15.7. In college algebra, you will do much more with this topic. This is just an introduction to the concept of functions. All right, well, we'll see you in the next video.